It's possible to use the transfer matrix itself to find eigenstates in cases of truly bound states. For example, if the first layer, layer 1, and the last layer, layer n plus 2, are infinitely thick and have potentials V1 and Vn plus 2, then there may be values of E that are below both of these for which there are bound eigenstates. So perhaps we might solve this problem and find a bound eigenstate with this energy and another one with this energy. The wave functions would be exponentially decaying into the first and last layers. That is, no matter what these particular solutions were, we would have exponentially decaying tails of some kind in here and exponentially decaying tails of some kind in there over on the right. So for the forward amplitude on the left, we would have to find that the forward amplitude, A1, was 0. Now, why is that? Because A1 being the forward amplitude would actually correspond to something that was growing like this. It corresponds to decay in that direction, so it would actually be growing like this. So that we presume is unphysical. We could only have something that's decaying down like this, and that would actually correspond to a B coefficient multiplying what is technically a growing exponential to the right, but is a decaying exponential to the left. So on the left here, for both of these solutions, we would have to find that A1, the amplitude just in here of the nominally forward wave, just to the left of this interface, would in fact be 0, because it would correspond to a wave that had decayed down to this point, or rather that was growing as we went off to the left. So no exponentially growing wave to the left of the structure as we go off to the left. And similarly, the backward amplitude on the right, Bn plus 2, would have to be 0, because we would only want an exponentially decaying wave going off to the right, no exponentially growing wave going off to the right. Well, if that is the case for some bound eigenstate, we would have that An plus 2 and 0, corresponding to just a decaying wave out there, multiplied by the transfer matrix, would have to give us 0 and B1, some finite number here. So we would have to have a 0 here, and we would have to have a 0 there, if this was a bound state. So for this transfer matrix, if this was to be a bound state, we would have to find that multiplying An plus 2 into this matrix gave us 0 in here, and possibly some other number down there. This can only be the case if T11 is 0. And this condition can be used to solve analytically for eigenenergies in simple structures, or in a numerical search for eigenenergies by varying E.